Hey guys, so I'm sorry I'm not here today, but I wanted to talk to you anyway, so we can keep learning about the diffusion and effusion of gases. So today we're going to start with just remembering the meaning of temperature, where temperature and heat mean very different things. They are related, but they mean different things. That temperature refers to the average kinetic energy of molecules as they are moving. They are related because as a gas is heated, it requires more energy, and so those molecules are going to be moving faster. So the more kinetic energy, the more the temperature will be recorded. It's a very important relationship because it summarizes the meaning of temperature of a gas. So it's basically an index of the random motions of the particles of that gas. So higher temperature means higher motion. In dealing with gases, this is really important. Because temperature means average kinetic energy, we can find its velocity. Now, knowing how fast molecules are moving is a special relationship, and for gases, we have to do that as a root mean square, or RMS, velocity. Um, if you want to look into that more deeply, the equation is derived in your textbook. But if we take the root mean square, we use the Greek symbol nu, and that means velocity, and then root mean square, we just write RMS under it. That equals the square root, right? So we're taking the root mean square of 3RT divided by the molar mass. Depends on the size of the molecules on how fast they will go. But before we use this equation, we have to be very careful because the R in this equation needs to be related to joules, because energy is related to joules. And so our R value has to be 8.31 joules per Kelvin moles. And that is how we must use this equation. So let's just do a quick example. Let's say a question asks us to calculate the root mean square velocity for atoms in a sample of helium gas at 25 degrees. So if we have a sample of helium gas at 25 degrees Celsius, how fast are they going? So our equation that we're going to use is this one right here. So the root mean square velocity is the square root of 3. The R we have to use has to be this one. Our T still has to be in Kelvin. So 25 plus 273 is 298 divided by molar mass. And so you also have to be careful with molar mass. Molar mass must be in kilograms per mole because joules are a unit that are kilograms meters squared per second squared. And so when it comes to the molar mass of helium, we know that it's 4 grams per mole. However, we need this to be in kilograms per mole. And so if I straighten this up a little bit like this, there are 4 grams in 1 mole. Grams goes to kilograms. And so for every kilogram, there are 1,000 grams. When I divide this by 1,000, I get 4 times 10 to the negative 3 kilograms per mole. And that's going to be the value that I need to use to get my root mean square velocity. So I'm going to put that number up here. 4, if you want to keep sig figs, 4.00 times 10 to the negative 3. When I type this in, I'll take 3 times 8.31 times 298 divided by 4.0 times 10 to the third. And then I need to take the square root of that. Don't forget to take the square root. And when I do this, because joules are in kilograms meters squared per second squared, the expression is going to be in meters per second. So when I take this value, you should get 1.36 times 10 to the third, and my units for the velocity are in meters per second. Okay. Moving on from velocity is talking about how we use velocity for gases in the process of effusion and diffusion. So we're going to start with diffusion first and then talk about effusion. So for diffusion, we're going to first talk about what that definition is. So let's start with diffusion. So diffusion is the term used to describe the mixing of gases. So we have two gases and we're mixing them. There's a really cool video on Canvas that I want you to watch because I don't have the right tube to do this demo for you, but it's really cool. So when small amounts of ammonia are released, it takes a while for everyone to smell that, or if someone farts, it takes a while for people across the room to get that full effect. So time is required for that gas to mix with the air. So the rate of diffusion is the rate of the mixing of gases. Effusion, so let's write that definition, is the term used to describe the passage of a gas through a tiny hole or orifice, which I think is a fun word, of an evacuation chamber. You can see a picture of this in figure 5.22 on page 220 in your textbook. But the rate of effusion measures the speed at which a gas will is transferred into a chamber. So this is gas through a tiny hole. A dude that spent a lot of time studying effusion was a guy named Thomas Graham. So we call this Graham's law, or Graham's law of effusion. And basically what Graham's law came into effect is that it only depends on the mass of the gas. So the rate of effusion for gas 1, so rate of effusion for the first gas divided by the rate of effusion for a second gas is equal to the square root of the mass of the second gas, see how these are opposite of each other, divided by the square root of the mass of the first gas. Okay, so if we're looking at this, let's do an example. Let's say that we have the ratio of effusion rates of hydrogen gas and uranium hexafluoride, which is used in the enrichment process to fuel nuclear reactors. So if we have hydrogen gas and uranium hexafluoride, we need to find the molar mass of each of these gases. So I can find the ratio by using Graham's law. Hydrogen gas obviously weighs 2 grams per mole. Uranium hexafluoride weighs 352 grams per mole. So they have very distinguishable molar masses. So to find the rate of effusion, which is just the rate of each of these over each other, I simply need to take the square root of the second gas, which is our uranium, 352, divided by the square root of our hydrogen gas, which is 2. When I take the square root and divide these numbers, you should get 13.2 as our rate of effusion. This is a unitless number. We can say that the effusion rate of very light hydrogen is about 13-ish times that of the massive uranium hexafluoride. So it just gives us the rate at which hydrogen is over the uranium hexafluoride. So how we can use this in Graham's law is also related to diffusion. So it's frequently illustrated by a demonstration where you can mix ammonia and hydrochloric acid to find sorry, I lost my train of thought. So using Graham's law, you can find the rate of effusion of a bunch of different gases. And that's all we need to worry about for right now. You should be able to then answer. There's separate links on Canvas for you, and there are different things for you to practice while I'm gone. Have fun and bring questions tomorrow.